There are a few elementary single-transistor amplifier configurations that serve as basic building blocks for all electronic amplifiers, even the most complicated high-performance ones. In this video, we're going to introduce those basic transistor amplifier configurations. On the left, we see the basic NMOS amplifier with input applied at the gate, lowercase VGS is the small signal input superimposed in the DC bias, uppercase VGS, and the output taken at the drain of the transistor, with the source connected to ground or some other DC reference voltage. Shown in the top right is a sort of shorthand small signal equivalent schematic, where we haven't yet replaced the transistor with its small signal model, but we have represented the small signal VGS as the input voltage VI, and we've set the DC bias voltages, uppercase VGS and VDD, to both equals 0. So the resulting small signal equivalent schematic shows the input at the gate, the output at the drain, and the source of the transistor connected to ground, which is a sort of common potential across the entire circuit. So therefore, this configuration is referred to as a common source amplifier. There are variations of this where the way DC biasing is applied may be changed, but the overall characteristic of the common source amplifier is that the input is applied to the gate of the transistor, the output is taken at the drain, and the source is connected to a constant DC voltage in the small signal equivalent schematic. A very similar configuration is shown here with an NPN transistor used. Again, its sort of shorthand small signal equivalent is shown in the bottom right. You see the DC bias voltages, uppercase VBE and VCC are set to 0 here. And in this case, with the NPN transistor, the input is applied to the base, the output is taken at the collector, and it's the emitter that's connected to the common, in this case, ground potential. So this configuration is called a common emitter amplifier, and it has many similarities to the common source amplifier. Now let's take the next step, and for the common emitter configuration, let's replace the NPN symbol here with its simple small signal model over here on the right, and we arrive at the complete small signal equivalent schematic. We've here included the source resistance for the input Rsig, which wasn't shown in the picture on the right. So if VI had an equivalent source resistance, Rsig, it would be right here, and Vsig is really the same as VI over on the left. We've neglected here the early effect, but we could incorporate it into the model with a small signal resistance RO connected between collector and emitter. So here's the common emitter node, and this is our pi model for the NPN transistor. A very similar small signal equivalent circuit could be arrived at for the common source amplifier. The main difference would simply be that our pi, which is the small signal base resistance in the NPN transistor model, is really an open circuit in the small signal model for the MOSFET. So it's like effectively setting our pi to infinity. But otherwise, you have a very similar looking small signal equivalent schematic for the common source amplifier, and all the following details of the analysis would be the same. There's different labels usually applied. Instead of Vpi for the MOSFET, we call it VGS, but it's essentially the same equivalent schematic for the common source. So once we've arrived at the small signal equivalent model, you can see it looks very much like the amplifier, the general amplifier that we're used to, unidirectional amplifier with an input on the left, output on the right, which we generally characterize in terms of its voltage gain and or its current gain and or its transconductance or transresistance gains, and its input resistance and output resistance. So we're going to be interested in those same amplifier properties for the common source or common emitter amplifier. What's its gain, what's its input resistance, and what's its output resistance? So if we wish to adopt a voltage amplifier model for the common emitter or common source stages, we simply need to find Rin, Ro, and voltage gain AVO for the circuit above. We're defining the input to the amplifier as being the base or gate terminal of the transistor, and the output as being taken at the collector or drain terminal of the transistor. So the input resistance Rin is just straightforwardly seen just by inspection to simply be the small signal base resistance R pi for the common emitter stage, as written right here. We'll just write that out again. A reminder, if we're talking about the common source, which I'll just abbreviate CS, remember that R pi is infinity, so the input resistance of the common source stage is infinity. The output resistance, recall, is found by setting all independent sources in the circuit to 0. In this case, the only independent source left in the small signal equivalent circuit is V sig. So we set that to 0. Apply a test source at the output. For example, a test voltage source, and look at the resulting current. So just quickly, if we do that, the schematic that we're left with looks like this. Here, V sig has been set to 0. As a result, there's no current flowing here. There's no voltage drop here, which means that the dependent current GM V pi is equal to 0, which means it's essentially like an open circuit. So all we're left with then, if we connect the test source to the output here, let's call the test source Vx, and find the resulting current Ix, obviously they're just going to be related by Ohm's law, by the resistance Rc. So the output resistance, Ro, of the overall amplifier is simply Rc for the common emitter stage. This, I believe, was labeled Rd in the schematic we looked at for the common source amplifier. So Rc for common emitter, Rd for common source. Now I should say that if we had included the early effect, or in the case of the common source stage, channel length modulation, then there'd be an additional resistance Ro here, in which case we'd have an extra sort of parallel resistance here, and the output resistance would be Rc in parallel with Ro. Okay, so the final amplifier, voltage amplifier parameter that we may be interested in is the voltage gain, AVO. That's the open circuit voltage gain. And that's simply got two components to it. First, it's the voltage gain from V sig to V pi. And then that times the voltage gain from V pi to VO. Now, V sig to V pi is governed simply by the resistive voltage divider, R pi over R sig plus R pi. Remember, in the common source stage, R pi is infinity, so that term would just be unity. Expression would simplify. Then the gain from V pi to VO is simply negative GM, because the current's flowing in this direction, generating a voltage drop across RC that's equal to negative GM times RC, possibly in parallel with RO if we're including it in our model. So that's the open circuit, the resulting open circuit voltage gain here. Again, remember, that's for the common emitter. For the common source, our pi is infinity. And we may have labeled RC differently, so it might be labeled RD. So those then are all the three parameters of a voltage amplifier. And so from there on, we see that the common source or common emitter amplifier can simply be thought of as a voltage amplifier with those parameters. Generally speaking, we see that the input resistance is fairly large. Our pi may be on the order of kilo ohms, and for the common source amplifier, the input resistance is actually infinite. The voltage gain also can be fairly high. GM times, it depends on your choice of the resistor RC as the designer, but you can realize a voltage gain there, a significant voltage gain. And the other term in the voltage gain, R pi over R sig plus R pi, can be made close to unity. And in the case of the common source amplifier, would indeed be unity because R pi is infinity. And then finally, the output resistance is set by RC. So if we have a high gain, probably means that RC is not so small. So the output resistance is not very low for this stage. So those are just, qualitatively speaking, the features of this type of amplifier stage, and that can dictate what it's useful for. Generally speaking, it's useful when we want a fairly high input resistance and some voltage gain, but it does not provide a very low output resistance. We'll need to use other amplifier stages for that. Now here's an example of the second type of basic transistor amplifier. You'll see in this case illustrated here with an NMOS transistor, the input is applied to the source terminal. The output is a gain taken at the drain, and it's the gate this time that is connected to a DC voltage, in this case again, ground. So there's a lot of other things going on here. There's some capacitors and a current source. So let's first take a step back and remember that when analyzing an amplifier like this, you first need to perform a DC bias point analysis. And when analyzing this circuit at DC, we know that all of the capacitors are open circuits. So we need not include them in the analysis. The input voltage, VI, is disconnected from the circuit, and we'd simply be performing an analysis of the following circuit. So the drain current, ID, would simply be determined by the current source I. The DC voltage drop between gate and source, VGS, would in turn be related to ID by square law that we're accustomed to. And so on. We could also find DC drain voltage here as VDD minus the voltage drop across resistor RD. So having performed a DC analysis like this, we would know the bias voltage at all these points. VD, Vs would be ground minus the VGS we calculate in the DC analysis. But then we, through those coupling capacitors, introduce a time-varying signal. So the signal to be amplified, Vi, is probably a small amplitude, time-varying signal whose frequency content is high enough that the capacitors CC1 and CC2 may be considered short circuits when it comes to performing the small signal analysis. So the key point here is that they serve as open circuits for the DC analysis, but short circuits for the AC analysis or small signal analysis. And here we're just performing the DC analysis for now, so let's leave them crossed out. So since the gate in this amplifier is connected to a DC voltage, in its small signal equivalent, it will be connected to ground, and we therefore call this a common gate stage. So this again is a simplified small signal equivalent where we haven't replaced the transistor with its complete small signal model, but we do set to 0 all the independent sources that have already been taken into account in the DC analysis. So specifically the current source I is set to 0, right? So it used to be here, but when we set a current source I equal to 0, it's the same as replacing it with an open circuit. And we've also, the other independent source that's relevant here is the supply voltage VDD. That's been taken into account in the DC analysis. So you'll see that here VDD is also set to 0. And so we end up with the schematic shown here. You'll also note here that the coupling capacitors CC1 and CC2 are assumed to be short circuits because it's assumed that at the frequencies that we're interested in, that is at the frequency, at the lowest frequency content of the signal Vi, those capacitors values CC are large enough that their impedance, which has a value of 1 over j omega C, is very small, so effectively a short circuit. So we have the additional assumption here that CC1 and CC2 are large enough that we can treat them as infinite, so we kind of replace them with short circuits here and here. And so having made all those simplifications, we arrive at this simple small signal circuit shown in the top here. And again, you'll notice that the gate is at a common constant voltage, so we call it a common gate stage. The input's applied to the source, the output taken at the drain. There is a very closely related stage shown below using a BJT called the common base stage. For the common base stage, the base is connected to a DC voltage, hence a small signal ground here. The input is applied to the emitter, the output taken at the collector. But again, a lot of similarities with the common gate stage, so we'll discuss them together. So we'll next go ahead and replace the NMOS transistor here with its T model, small signal T model, shown here. We're here ignoring the channel length modulation. So we're excluding RO from the picture, the assumption being that RO is fairly large and can therefore be safely ignored. In fact, including RO does significantly complicate this analysis, so it's convenient to ignore it. But you can take it as an exercise to try to perform a more rigorous analysis, including RO. If you did, of course, RO could simply be included like this. But let's ignore it for now. So in this case, if we want to model the stage as a voltage amplifier, we may be interested in its input resistance, Rin. This is found straightforwardly just by inspection of the circuit. You see that the current I labeled above is the input current to the amplifier, and that's just determined by Ohm's law across this small signal 1/GM resistance. So VI. So Rin being the ratio of VI over the current going into the amplifier, which is actually negative I, we see that we've simply got an input resistance of 1/GM. This is a very small input resistance, so we don't usually use a common gate stage as a voltage amplifier for a source with a large source impedance. If we had a source impedance here, sort of R-sig in series with the input source, then you get a large voltage divider formed between VI and the gate source voltage, small signal VGS. So you'd lose a lot of the input signal just through that voltage divider. So often may not be the best choice for a voltage amplifier with a voltage source having a high source resistance. The current I in this model simply appears as a drain current. So the output voltage VO is negative I times the drain resistance RD. If we substitute in this expression for I, you end up with GM RD VI, and rewriting that as voltage gain. You see, you end up with an expression that's very, very similar to that of, for the open circuit voltage gain, to that of the common source amplifier. The main difference just being that in the common source amplifier we had negative GM times RD, whereas here we've got positive GM times RD. So like the common source amplifier, you end up with a large voltage gain. And then finally, the output resistance, if we're interested in that, the small signal output resistance, looking into the amplifier here, could be found by applying a test source here and finding the resulting input current with VI set to 0. Now with VI set to 0, the small signal drain current in the MOSFET would be 0, so there would be no current flowing into the drain of the MOSFET, and therefore you simply have an output resistance of RD. There'd just be nothing else connected to the input. So those then are the parameters of the common gate amplifier. Here's the input resistance, the voltage gain, and the output resistance. Again, in many ways, it's similar to the common source amplifier. The main difference is that with the common source amplifier, the input was applied to the gate. So we saw a high input resistance, whereas here it's applied to the source. So we see a low input resistance. That also creates a sign inversion when it comes to the gain. Right? Instead of a negative gain, we've got a positive gain now. But in any case, it's in many ways similar. There's a lot of similarities anyway between the common source and common gate amplifiers. The most important difference just being low input resistance instead of high input resistance. Next, let's consider a BJT amplifier in this family. And just to mix things up a bit, I'm going to show an example using a PNP transistor instead of an NPN transistor. Now, the BJT analog of the common gate amplifier is the common base amplifier. In a common base amplifier, the input is applied to the emitter. It's the base that's connected to the common or DC voltage, which looks like a small signal ground, and the output is taken to the collector. So again, very similar topology to the common gate. But in this stage, over here on the left, it's a specific example of a common base transistor, a common base amplifier where we're using a PNP transistor. But we still see that it's a common base because it's the base terminal that is connected directly to a DC voltage, again, in this case, ground. And again, the input's applied to the emitter. It's just that we usually draw PNP transistors with the emitter on top because they're generally biased at a higher voltage than the base. So the input is applied to the emitter, just as in the picture shown here. The output is taken at the collector, just as in the picture over here. Now, an important difference between this particular example of a common base amplifier and the example common gate amplifier we showed earlier is that here we've got a resistance RE connected to the emitter, whereas the NMOS example that we looked at before had a current source, a DC current source setting the bias current in the transistor. So whereas a DC current source looks like an open circuit in the small signal analysis, a resistor still looks like a resistor in the small signal analysis. So we've really here should still show the resistance RE when we're moving towards our small signal analysis. But otherwise, a lot of similarity. The capacitors CC1 and CC2 are assumed in the small signal analysis to be large enough that we can consider them short circuits. So they're here replaced with short circuits. And we've also set the other independent sources to 0. So these are the supply voltages, V plus and V minus. They would otherwise appear here and here. So the final step moving towards a small signal schematic is to replace the transistor here with its small signal model. Again, we're using a T model here. Now you might say, wait a minute, I flipped the transistor type around as I move from left to right here from PNP to NPN. But remember that the small signal model for PNP and NPN transistors are the same. So shown on the right is the small signal equivalent schematic. Of the common base amplifier shown on the left. Now, as you get more practiced at doing these small signal analysis, you may be able to write down some results without having to solve a bunch of nodal equations. At first, as you're just doing these types of problems for the first time, you'll want to do a detailed nodal analysis to get the results. But again, with time, you'll come to recognize things more quickly. So for example, in this case, if I'm interested in the input resistance, looking into the amplifier here, right, that would be the input resistance, looking into the amplifier here, you can recognize that between that input node and ground and small signal ground, you see simply RE, this resistor here, in parallel with the small signal emitter resistance, RE. No need for a detailed analysis there. It's quite evident that those two resistors appear in parallel in the small signal schematic between the input node and ground. Similarly, if we're interested in the output resistance here, we've here again neglected the early effect, just as we did in the common gate stage, to simplify the analysis. So when finding the output resistance, we would set VI to 0. And doing so, we would have no current, no collector current in the BJT. And as a result, the output resistance would simply be RC. And then the last amplifier model parameter that we might be interested in finding is the voltage gain. So to find that, we should first recognize that this current IE is simply given by the voltage across the resistor, RE, which is VI, divided by that resistor value RE. Now the way we're defining the polarity of the small signal current, we generally define it as being the small signal current coming out of the emitter, so there's a minus sign in this expression to account for that. Then that current IE, some small fraction of it, 1 over beta plus 1 times IE flows in from the base, but the remainder, alpha times IE, flows in from the collector. So the output voltage here is simply alpha times IE, creating a voltage drop across RC. So we have to multiply by negative RC because the current's flowing up from ground. And when we substitute in our expression for IE, we end up with this expression relating the small signal output voltage and small signal input voltage. So as a result, the small signal open circuit voltage gain is simply alpha RC over RE. So there's the parameters of our amplifier model: the small signal voltage gain, input resistance, and output resistance. In general terms, again here we see a relatively small input resistance. In particular, the small signal RE of the transistor, lowercase RE, is likely to be a small value. The output resistance can be fairly high if we choose RC to be fairly high. The voltage gain can be quite high as well. Again, if we've chosen RC to be a large value, then the ratio RC over RE is likely to be large, give us a significant voltage gain. Alpha will be close to 1, of course. So very similar to the common gate stage. It's a lot of voltage gain in general, and a fairly high output resistance, but a very low input resistance. Here's an example of the final basic transistor amplifier configuration. Shown here is an NMOS example. And so in this type of amplifier, the input is applied to the gate, the output is taken at the source, and the drain is connected to a DC voltage. In this case, it's a supply voltage, but since it's a constant DC voltage, we're going to take it into account in the DC analysis, and then when it comes time for the AC analysis, we're going to replace it with 0 voltage source or ground. So therefore, we refer to this stage as a common drain stage, and we also commonly refer to it as a source follower. You'll see why as we do the small signal analysis. So as always, with an amplifier like this, the first part of the analysis would be to find the DC operating point. So the gate voltage here would be a superposition of a DC voltage uppercase VI and the small signal VI superimposed on it. The DC bias VI would give rise to a DC voltage drop VGS across this transistor and a DC drain current uppercase ID. And so those could be solved for assuming the small signal lowercase vi is 0 at first. Having done so, then we can linearize the transistor. In that initial analysis, since it's a DC analysis, we would assume the capacitor is an open circuit. Then having completed that, we will move towards the small signal analysis. Where we then assume that the capacitor is a large enough value that it may be considered a short circuit at the frequency of our small signal input Vi. And we also assume that the supply voltage here, VDD, is set to 0 in the small signal analysis. And of course, the DC bias at the input, Vi, is set to 0 as well. So we're just considering the small signal part. So we can next go ahead and replace the MOSFET with its small signal model. And in doing so, we arrive at a schematic like this. I'm going to use the T model again. So there's our transistor model. GM VGS here. Here's VGS. And then we've got the load resistance RL and the small signal output VO. So the analysis of this very simple version of the circuit is pretty straightforward. Essentially, between the input and output, the gain is nothing more than a resistive voltage divider in the small signal equivalent schematic between RL and the small signal resistance 1 over GM. We can rewrite this as GM-RL over 1 plus GM-RL. So as long as we select, as a designer, select the parameters of the transistor, that is, select the transistor to have a value of Kn, and define the DC operating point appropriately and the value of RL, we can ensure that GM-RL is much greater than 1, and in doing so, we would see that this circuit has a voltage gain very close to unity. Very close to, but slightly less than unity. So effectively, with respect to the small signals that are superimposed in the DC operating point, we would see that whatever signal arises at VI, VO would simply follow it up and down with a gain very close to 1. That's why we call it a source follower. The source follows the gate voltage up and down. But so you might say, well, how is this stage useful or interesting if it's just providing a gain of 1 and in fact slightly less than 1? Well, obviously we don't use it as a voltage amplifier to increase the amplitude of a voltage signal. But don't forget that thanks to the dependent current source in the T model, there's no current flowing in here. So this stage has a very high input resistance, ideally infinite. Moreover, it has an output resistance, especially if we consider it looking into the transistor. If we consider that the output of the amplifier, and we consider the resistor RL as simply part of the load, then the output resistance is very low, 1 over GM. So it has some properties that make it different from the other two types of stages we've seen so far. Although it has a very little or no, effectively no voltage gain, it has a combination of high input resistance and low output resistance. So this makes it very useful as a voltage buffer. So when we need to drive a resistive load, especially one with a relatively small value in ohms, and we need to connect that low value resistive load to a source with a large source impedance or source resistance, then a stage like this can serve as a buffer in between that prevents a large voltage division ratio from arising between the signal source resistance and the load resistance. So in summary, this type of stage is primarily useful as a buffer with a gain of about unity. Now, again, as we have for all the stages so far, we've neglected the output resistance RO. In this case, it's actually pretty straightforward to include it. It would simply show up here between the output node and a small signal ground. So it would simply be in parallel with RL. It would be an extra term as well in the output resistance. But it wouldn't, since it's much larger than 1 over GM, it wouldn't have much effect on the output resistance either. So yeah, it's pretty easy to include that in the analysis in this case. We've also here neglected the body effect. In this particular amplifier, the body effect can be of interest since you'll notice the source voltage is moving around. So if the body voltage is connected to a constant DC voltage, then there will be a change in the source body voltage, which will have an impact on the performance of the stage. Let's just leave that as an exercise for now. Here is a BJT equivalent of the source follower. In this case, we would call it an emitter follower. You'll notice that the input here is applied to the base. The output is taken at the emitter, and the collector is connected to a DC bias voltage, which is essentially a small signal ground. Now in this schematic here, we're showing a lot of details, a lot of extra components, resistors that are required to establish the DC operating point. But essentially the key features are still there. That is, the collector is connected to small signal ground, as pictured here. So we call this stage a common collector stage, or we will often refer to it as an emitter follower, because like a source follower, we generally find that the emitter voltage follows the base voltage in the small signal equivalent schematic. Now, a DC analysis of the circuit would look like this. We've simply got RB connected between ground and the base terminal. And RE connected between the emitter and VEE. So we could solve this circuit, find the resulting collector current, for example, assuming a constant forward voltage drop of about 0.7 volts across the base emitter junction. And once we know the collector current, we can find things like the GM of the transistor, its R pi, and so on in the small signal model. Then we'd move to the small signal linearized analysis. This is the MOS version, so the BJT version is shown there at the bottom. And as you can see on the left, the particular example here includes a source resistance, R sig, in series with the input V sig, and a base resistance RB. And these resistors appear both in the DC analysis and in the small signal analysis. The capacitor CC1 here is assumed to be large enough that we may consider it a short circuit in the small signal analysis. Likewise, capacitor CC2 is considered a short circuit, whereas they are open circuits with respect to DC. So they're ignored in part one. The load, with the CC2 being a short circuit, the load resistance RL here is actually the parallel combination of RE and RL. So let's call this one RL prime, really the combination of these two here. So that's the sort of simplified small signal schematic. And so the analysis is a little more complicated than what we performed for the source follower, because there's a voltage divider set up at the input between R sig and RB and R pi. But generally, the analysis looks very similar once we find the small signal base voltage here, VB, we would find that the output voltage follows VB very closely. And so again, we've got a stage that provides near unity gain with a fairly high input resistance, because looking into the base of the BJT, we have connected our pi, which is a fairly large resistance, and a small output resistance, because looking into the emitter of a BJT in active mode, we see the small signal resistance RE of the transistor, which is quite small. So it has very similar uses as the source follower. Again, it serves primarily as a voltage buffer. So just to recap, we looked at 3 types of single transistor amplifier configurations. On the left, we see the common source or common emitter amplifiers. These are characterized by a relatively high input resistance. So looking in here or here, we would see in the case of the common source an infinite input resistance. In the case of the common emitter stage, the small signal R pi of the BJT. These are also characterized by a not too small output resistance, determined primarily by RD in the case of the common source, RC in the case of the common emitter. We're here neglecting channel length modulation and the early effect. If we were including them, they would appear in parallel with RD and RC. And finally, a modest to high open circuit voltage gain given by negative GM times the output resistance RO defined above in both cases. Second class that we looked at is the common gate or common base stage, shown here in the middle. These are characterized by a much smaller input resistance. Looking in here or here, we see in the case of the common gate stage, just 1 over the small signal transconductance GM of the transistor. And for the BJT stage, it's actually alpha over GM, which alpha being very close to 1 is a very similar input resistance. And we also use the small signal quantity RE for that. And these have an output resistance similar to that of the common source and common emitter stage. That is, it's RD in the case of the common gate stage, RC in the case of the common base stage. And finally, we also see a relatively high open circuit voltage gain, but in this case, it has a positive polarity, positive GM times RO in both cases. Finally, on the right, we've got the source follower and emitter followers. These, you may recall, serve primarily as voltage buffers because they offer a fairly high input resistance. Looking into the amplifier terminals here, infinity in the case of the common or drain stage or source follower. We didn't do a detailed analysis of the input resistance of the emitter follower. It turns out it's R pi, which is not surprising because we're looking into the base terminal of the BJT, but there's an extra component that depends on the load connected at the output. So in the case pictured here, it would be beta plus 1 times RL would be this extra term. So in any case, that certainly adds up to a fairly large input resistance in the case of the BJT emitter follower. The output resistance, however, in both cases is very small. Let's here define the output resistance, again, looking into the terminal of the amplifier as we've defined it in these pictures. So in that sense, the output resistance is similar to the input resistance of the common gate and common emitter stages, because we're looking into the source and emitter of the transistor. So 1 over GM in the case of the MOSFET, and alpha over GM or RE in the case of the BJT. And finally, a voltage, open circuit voltage gain close to 1. It's just determined by the voltage divider between the output resistance and the load. And we expect that to be close to unity.